I've been playing around a bit more with this little UPS board, DC-DC UPS board. And I'm just curious as to see how the battery protection works on it. So at the moment it's hooked up to 9.2 volts from a power supply. It is currently charging this old power bank battery from a failed power bank. The battery didn't fail, it seems in nice shape. It's driving one of my little 9-volt bulb or 12-volt bulbs there at the end. And currently it is charging, let me slide the light over a little bit, charging the battery at 178 milliamps. Well, I'm not quite sure how accurate the unity meter is at this, but it's good enough for this. What I'm going to do is I'll slide out so you see what I'm doing. So there's a little load of, I don't know, a few milliamps on the circuit. It's supposed to be outputting 9-ish volts. And what I'm going to do is disconnect the power. Light stays fine. And we'll note that we're now drawing, this was showing negative current before, it's now showing positive current at around 69 milliamps. Right, we'll plug it back in, we'll put 9 volts back on the board. It swings around, it goes to negative. It went to 200 milliamps. And now the charging current's going down a little bit. So the interesting question is going to be, what happens when it stops, and at what point does it stop draining the battery? I haven't been able to identify the battery protection chip, and this is an unprotected battery, which makes me a little nervous, but it's what I had that was convenient. And this would be a nice pairing with this board. I'm sure it's not 4,000 milliamp hours anymore, but might have been when new. I think the claim on the battery pack was that it was 6,800 milliamp hours, which actually suggests this is probably honest. People who manufactured the battery pack, not maybe so much. Anyway, so we've got the board, we've got a small load. It does function as advertised quite well, really. You can see the charging current's dropping a little bit. And so what I'm going to do is I'm going to let this run. The meter will unfortunately shut itself off in a bit, but I'm going to let this run and try to charge up this battery, and then we'll see what happens when it stops. What I would like to see is I'd like to see no current within what this meter can handle. And then what we'll do is I'll disconnect the power supply and I'll let it run down with this little bulb, and we'll see. This thing has been stored for years and still had it over 4 volts on it. In fact, it had enough to run this circuit, no problem. So the battery, despite my not storing it very carefully, ended up just fine. So I think we should assume that that power pack is good, and we'll see what this does. Oh, I'm not sure I said before, but I tried to identify the chips on this board, and what I was trying to identify was the charge controller, or the battery protection chip. This one on the back has, this is the circuit from the original power bank, and something on here is bad, which is what was causing the problem. But on the back of it over here, there is a little chip. Got the wrong way around. This little chip there, which is the charge controller, and I can't remember what it is, but it's one that Big Clive has talked about many times. And I was hoping that I would find that on this board, although I'm somewhat hopeful that that one there is the equivalent. It's in about the right place, and yeah, so, but searching its number yielded nothing. There are 2 power controllers. There's one here, and there's a bigger power control chip here. I think this may be MOSFET or something. I couldn't quite find that one either, or a regulator or something. I don't know. Anyway, so I'm just going to have a look at its behavior, and then that will give me some idea of whether I feel safe using it or not. Well, I will be back when I have some idea of what's going on. So I'm still trying to run down the battery here on this little setup. It draws about 132 milliamps from this battery, where if you do the math on the 4,000 milliamp hours, you can get some idea of how long it ought to go. Let's just do that. So keep in mind that this is certainly wrong, but if we take 4,000 milliamp hours and we divide it by 132, which is what I measured across, well, one of those leads, we get 30 hours. I originally had one bulb on, but that would have led to, well, twice that, 60 hours. Now, that's interesting because we can also do some other math with this stuff. So we could look at, so we know that last I checked was at about 3.9 volts. So we could do 3.9 volts times that 132, and we get 515 milliamps. So, I'm sorry, 515 milliwatts. So we're pulling about half a watt out of this battery. Now I have measured the amperage through these little bulbs, and each of them is about, oh, if I remember, we'll say 0.025. I think it was a 0.024. Well, let's put it in the way I remember it. Clear. 0.024 times 2, so 0.048 for the two little bulbs, and that's at 9.2 volts, which equals just under half a watt. So actually, if you take that and you take the 550, you can make an efficiency calculation for this little circuit. I'm sure the voltage on this has dropped a bit since then, so it's probably pulling a little more current to produce this, the result we had here. Sorry, I pressed the wrong key. So that gives me some idea. I'm gonna let this run. I'm curious to see what happens when the battery shuts off. It should presumably shut off. I should be able to test no current, and then we should be able to plug it again to reset the circuit. I did accidentally short these briefly while I was putting the second bulb on, and it shut it down, and I had to reapply external power, of which there is none at the moment. You can see the little power supply is not plugged in. So we're going to run that down and see where it stops pulling current out of this battery, and then I will plug it back in and we'll find out at what voltage it stops charging this battery. I'd started to do it the other way around and realized that was foolish. So my suspicion is that this is going to run down at some point tonight, and we'll see. So apologies for the sound of the dryer in the background, but the lights have shut off here. So let's see what the voltage is on this battery. I'm not sure I can do that and hold this camera at the same time. We will see. I think the answer is no, so I'm going to check. The meter has just started up. I will check and report back. All right, so what it showed on the meter was 2.9 something volts. So it obviously shut off as soon as it went below 3 volts. That's good. If we check the current flowing through the battery, it is now 0. So now what I'm going to do is I'm going to plug in, let's see if I can do this with one hand, this little power supply over here. I believe this is hard to do. Okay, so that's now putting 9.2 volts out. The bulbs have turned on, and we should now see a negative current, right? So we see a negative current 434 millivolts, which makes sense going onto this battery, and these little lamps are now being lit by this power supply, which is also charging this battery. So that means that if we were to take this clamp meter off of here and put it around one of these leads, keeping in mind that I haven't zeroed it and I've moved it, we see 300 milliamps or so at 9.2 volts. Let's see. Yeah, you know, a little higher than that because it's not zeroed for over there. Every time you move one of these things with a Hall effect sensor in them, you've got to re-zero them. It's fairly irritating, but they're only for rough and ready measurements, really. Yeah, that's consistent with what we had before. I have tested it before, and I know it's producing 4.2 volts on the, or it was on the output, which is reasonable. So now we'll leave this. This should be in the constant current charging phase of the lithium battery, because these go through a constant current charging phase, and then they go through a constant voltage phase. Actually, the voltage may be higher. Let me check that just a moment. So I was correct. The current is not, the voltage is not higher, the voltage is lower. It's 3.3 something volts, which is reasonable since it's trying to drive a constant current into a cell. So there's no question that we've got constant current regulation of the power supply. So this does have a charging chip in it, because I know earlier on when the voltage in here was over 4 volts, it was producing 4.2 volts, and the current was changing as the battery charged. So there's certain currents, definitely a charging chip of some sort in here that's controlling the charging of this. Now the only thing that I'd like to see is when we get cutoff of this battery, and we should see it cut off somewhere around 4.2 volts. So we'll see how that works. That will be interesting. So the main thing we'll see is that the current on the battery will go down to 0 once that happens. So we'll see no current in either direction on the battery. It will be essentially out of circuit, and these bulbs will still be driven directly by the power supply through the circuit here. All right, we'll check that out. So I want to note one more thing. This board ran almost completely cool before, but now it's quite warm. The inductor's a little warm, but there seems to be warmth coming from some of these chips. But it's, anyway, the whole thing's now running a bit warm now that it's pushing a bit more current. It was dead cold before. Interesting. So here is the battery, and it is now showing no current. That's within error of the clamp meter. There's nothing flowing through. And a good trick, I knew this was going to be the case, is I felt this board, no warmth, and I felt this one, and not much warmth. So obviously no current was flowing through this side of the circuit, or relatively little. So we'll take this off now that we know. You see it's bouncing around between 1 and -1, so nothing. Now I'll take this meter off, and I will go, I can't do this on screen, but I will go and check the voltage with the voltmeter. So I checked the voltage with the hand check, and it says 4.16 volts. So it's clearly stopping the voltage it's clearly stopping the charging at 4.2 or something like that, or slightly below. If it starts at 4.2, it's not, well, you wouldn't, it might fall down to 4.16. So I think we see a proper charging cycle from this little board, It's running a constant current at a little over 400 milliamps and for the first bit, and then it gradually runs at constant voltage for the last bit and stops out right around 4.2 volts or slightly under. That's pretty good. So the next step is going to be to disconnect the load and disconnect the power supply and just get some idea about how the battery drops over time. And I'll just make some notes to try to keep track of what's going on. So I'm just, what's the quiescent current of this? And I don't think my this is going to be able to read it, but we'll see. If we could just get even an order of magnitude on the quiescent current with still voltage on this line, then we have some idea of how long, if you were to install this into, say, a boombox, which is what I'm planning to do, how long it will run. After that, the next step is to try an unregulated power supply on this end to see if it plays nicely with an unregulated power supply. Because if you're going to put it in an old boombox, it'll be an unregulated power supply at that end. And if it plays nicely, it might give us nice regulated power out of this end. Maybe, we'll see. That will be a later step. Okay, I've got it hooked up, nothing plugged into it, no load. And it's saying 3, 2, 3, 400 milliamps. 3 seems to be about the average. Let's slide this off and see where I am calibration-wise. Totally off. So let's try that again. Oh, there we go. -1, okay, let's zero that. Let's see, can I do this with one hand? No, just a moment. Okay, I zeroed it and slid it in and I'm getting 0.02. So I'm going to consider that that is probably what it's drawing. Well, maybe give it a little longer. I mean, I could desolder one of the links and put another multimeter on. I may do that later. But let's see, let's do the back of the envelope calculation. Let's assume that this battery meets its rated amount. So it's 4,000 milliamps hour. We'll turn on calculator. So 4,000 divided by 2 equals, so that's 2,000 hours divided by 24, 83 days before it goes completely dead. I think we can probably live with that. Of course, I wouldn't assume that this battery is anywhere near that, but this does actually seem to be kind of in line with modern electronics, which is, you can leave it for a month, but it's going to be pretty close to dead after that. So I'm thinking that might be okay. Well, not being happy with the ammeter on this for doing these low readings, I hooked up the Handtech across in milliamp mode, and it sort of fluctuates between 0.22 milliamp hours and 0.11 milliamp hours, which it drops back to. I don't know if the switch between them has to do with the processor going in and out of a cycle or not. But I did the math on assuming it's, sorry, that was going to be so I did the math. So let's do the math. Assuming 4,000 milliamp hours and divided by 0.11 milliamp hour, that gives you about 36,000 hours, which is 1,500 days. If we treat this as 0.22 milliamp hours, which is what it's currently reading, then you can have that. So 750 days. Big deal. Short answer is this battery and this power supply will work in terms of providing the 9 volts on the output for a long period of time. So that will bring us to step 2 of my analysis, or the next step. Since we know what the quiescent current is, we'll say 0.22 milliamp hours, which is an order of magnitude below what I was getting with this meter. So we'll see if it plays nicely with an unregulated power supply. And that will be our next step. So this is the power supply I intend to use. This is 1980s unregulated power supply. I've currently got it set up in center negative mode. So you'll notice that I have this plug tacked on here, but I've got it tacked on backwards because I want to be able to put it back on the other power supply when I'm done. So what I'm going to do is plug this in here, and we'll keep an eye on the voltage there, and we'll also put the oscilloscope on to have a look at what it goes, at what the waveform looks like and see what it's doing. Okay, so it's on. What we're seeing on this looks like unregulated. That looks like about the voltage drop across the diode. So obviously when the power in matches the power out, it's not doing anything. This thing does tend to go up rather high. Let's put some load on it and see what happens. All right, so I've got 2 of my 12 volt bulbs across, and we know that at 9.2 volts, that gave us about half a watt. So they'll be a little higher at this voltage. Up here, we can see that the voltage is down to 12 volts, which is interesting. Again, that wouldn't be a problem in most of these situations because because we'd be looking at the output of the transformer the radio was designed for. But this transformer does run up quite high. So let's have a look and see whether the battery's charging. So now we're looking at the battery. We still got the load on there, and the battery is charging at 4.2 volts. So that probably means that the power supply has shifted into constant current, constant voltage charging, I mean. So let's have a look with the little clamp meter. And we can see that's the case. It's now putting a charge into the little battery. So it does appear to be working. What I'm going to do is put these back on the output and see what it does when you unplug the power input. So let me show you. I will unplug the power input, and it goes to 9.2 volts. And plug it back in, it'll go back to the 12. So what it's doing is it's switching out, so it's not regulating the power in as long as it's over the threshold. So in fact, apart from the charge circuit, this board is largely out of circuit, and it just uses the power supply, but the charge circuit is still working. So what does that tell us? That tells us that this board will in fact work with an unregulated power supply in the kinds of scenarios, i.e. sticking it in the back of an old boombox, that I'm thinking of here. And so I think it might be time to actually try it. So here's the setup for the test. you'll notice that the colors on these are reversed. That's because both of these plugs are wired center negative as opposed to center positive, because that's what I'm connecting it to, and this is the power supply for that. We have this all hooked up. I've double checked that this is okay. So we've got the battery on it, and I'm going to plug it into my Sanyo boombox, and we'll see how that works. So here is the Sanyo, which I've repaired in a previous video. Just to show you that it's not turned on, we'll put the function to radio and nothing happens. That is functionally the power switch on this. So what we'll do is we'll plug it in on the side and give it a go. So there it is, it's plugged in. This is the power supply. I typically use it with it. Up a little loud. So it's Jazz FM, French CBC, music. That's probably English CBC music. Don't know who else would be playing Tom Waits right now. All right. So, no obvious problems on FM. We'll flip it over to AM.
Narrow, but a bunch of focus to just keep playing. I like college football a hell of a lot more. Some clarity on whether it had to be.
That noise is probably just from the computer equipment at my desk.
One of the more important aspects of the job. We also have a few showers in the morning across the GTA.
It's having no problem pulling in
afternoon, and then we do have some more chances for rain.
Strong AM stations, and it's not going to do very well on AM over here. Okay, so let's put it back to FM, and we'll pick something that will hopefully avoid. Go back to opera. That's less likely to generate a copyright strike. So let's unplug this. Okay, well, you could tell the voltage went down. Let's see. I'll try to plug it in again and see if you can notice. Okay, let's look at the battery light. See, dimmed a little bit when we went down to 9 volts. I should check the voltage on the power supply. So now we're running off of this battery. I mean, honestly, proof of concept. It works. Okay, I just want to check the voltage on that and get a tape, and we'll try those two things. With it just on radio, let's turn. With it just on radio, there is no question that the power supply is rock solid, turning it up until it clips. Let's get a tape. Okay, so a tape's in. You can look at the voltage and turn up the volume. I'll only do that briefly, but you'll notice that the voltage remains fairly steady. If you turn up the bass a whole lot and jack it up all the way, you can make it go down a couple of millivolts, but no problem. You can see as you turn it up, you can see the current draw go up on the battery. And if we stop the tape deck, we get some sort of residual draw there. If we go back to radio, so it looks like the tape motor costs you about 100 milliamps over and above this. And then most of the rest of the draw is going to be the amplifier. So if we assumed using it with a tape DAC that it would draw about half an amp, then we can do our battery life calculations based on that. Obviously, that's as the battery goes down in voltage, the current draw will go up because this little power supply will pull more. And but you know, rough and ready, that'll give us a baseline calculation. So we'll come back and do that, but I think my initial assumption is this little power supply will work. I don't hear any noise. Now, maybe if it's inside the case, it will cause problems, but so far, so good. So there's the board, removed. I'll have to take these plugs off because they're backwards. That's going to be confusing to me later. But the basic numbers are very promising. Assuming this battery is really 4,000 milliamp hours, or close to it, depending on your radio only, it should run for about 11 hours. Tape, it should run for about 8 hours. That's pretty impressive, really. That's entirely in line with what we would expect from modern equipment today. Now, unfortunately, this battery is too large to fit in the Sanyo. So in the battery case of the Sanyo. So if I were to do it in the Sanyo, I would have to mount it inside the case, which there probably is space for, but I'm at the moment still a bit reluctant to do that. So I think I'm going to put this in the Panasonic. Now, the advantage of the Panasonic is that it already has a line in, so it doesn't have to be modified to take a line in. I mean, I do think adding this to the Sanyo would make for a very sweet device. And so we'll see. If it won't fit in the Panasonic easily, maybe I'll try that. Anyway, so this is the last video I think I'll do, just looking at this little battery board. All the information I have on it is here. If you search for DC-DC UPS on eBay, you should be able to find it, this DC UPS version 1.0. I think to make it operate at 12 volts, you close that jumper there. I did speculate that it needed a resistor, but I think there's a whole resistor set here that looks like it's controlling the voltage it's set at, and I think that jumper will do it. I have not tried it. I'm also curious as to whether this says plus, minus, green, and red. I wonder if that, yeah, you see, look, those run down to this chip here, which I speculated is the charge control chip. I bet those are LEDs. So you could mount a charging LED on them if you wanted to at some point. This is a very interesting little board. Well, I'm going to try it out in the Panasonic. That'll probably be a separate video, and see how it works. If it works, then I may buy another one and use a different format battery and consider mounting it in the Sanyo, so one way or another. All right, well, I hope that was an interesting video, and thanks for watching.